Welcome back. Now, in previous videos, we've talked quite a bit about PDDs, percent depth doses. You've learned how they depend on energy, field sizes, and so on. Unfortunately, the PDDs are not really useful for modern treatments for reasons that I'll explain in this video. But the basic reason is that they're not useful for isocentric treatments where you have an isocenter at a machine that you're setting up to and treating there. So we need to define a new quantity called the TMR, the tissue maximum ratio, and I'll go over that in this video and explain what it is, and then in the next videos you'll learn more how you use it to do calculations. All right, here we go. So I'm going to have to start by looking at the PDD, and we talked about this a little bit back in video 10.2, but if you'll allow me to redraw this here, I'd like to discuss it in more detail. Here's the PDD for this particular setup here. So again, this is allows me to find the value at any depth D. I go over here, say it's 10 cm. I can look it up, find what the percent depth dose is there. In the special case, where I'm here at D max, the PDD is 100% by definition. So that's down here at D max, DM. So let's look at the fall off region of this PDD curve here. So first of all, there's the effect of attenuation, so e to the minus mu x. That's just the beam being attenuated linearly. There's also effects from scatter. We talked about that last time. There's effects also from inverse square. This last one is particularly important as we talk about this. So you'll go back, remember this discussion. This was showing that the dependence falls off as 1 over r squared. It's because the area falls off. And that's from video 4.2, so you can go back and review that if you need to. So because of this inverse square effect, it's going to have a difference at a different SSD setup. So if I'm here at SSD2, this curve is going to look different, okay? Because of inverse square, the curve will not look like this blue curve. At the beginning, it maybe looks similar, but then as you go down into this region, it falls off less steeply for larger SSD. So this would be the curve, the PDD curve for SSD2. So this is pretty important. So let me try to illustrate this another way. Imagine I have a point source here, and I have the blue circle where I'm very close to the point source. In this case, the fall off as I move out is going to be relatively large. It's relatively dramatic. As I move out, say a centimeter, I get lots of fall off. Compare that to another case where I'm sitting away from some source at a larger distance, and the fall off is less dramatic. As I move away a centimeter, say the inverse square fall off is not very big. So that accounts for this SSD dependence. So I can actually write a formula to account for this and convert between these. So let me show you that. So if I want to know what the PDD is for setup 2, I multiply it. I take some factor, SSD2 plus D max, divided by SSD2 plus D, that whole thing squared, and I multiply by another factor, SSD1 plus D over SSD1 plus D max squared. So, and times the PDD in setup number 1. Okay, so that allows me to convert this PDD to this PDD at 1 to 2. This factor is called the F factor. It's called the Maynard F factor. And it's a little bit hard to remember, but you don't really need to memorize this. You can kind of work it out if you know whether it should be larger than 1 or smaller than 1. So the Maynard F factor for setup 2, where the SSD is larger, should be larger than 1, because you know the PDD in setup 2 is larger than the PDD in setup 1. So you can kind of remember it that way. So now let me start to describe how this plays out clinically and getting on to dose calc. So I'll do this through a case study here where I'm showing treatment of a patient to a vertebral body at isocenter of the square. If I set up an AP beam to that position, it would be set up in this example at an SSD of 80. If I swing around to the posterior beam here ends up being SSD 95. So going here to 80, I know what the PDD is. I can go look it up. But the problem is, from our discussion before, you know that at 95 SSD, the PDD is going to change because that PDD is dependent on what the SSD is. So this is not a very convenient situation for doing an isocentric treatment because you can't just look these up in a table. So the solution is to not use the PDD at all, but instead use another quantity that's called the TMR, the tissue to maximum ratio. And I'm going to walk through what that is now. So the key to this is, instead of fixing this constant SSD in the setup like we've been looking at so far, we're instead going to fix this point here. That's the isocenter, the point where the gantry rotates around. That's typically how we do treatments. And then we can change the distance, the SSD, in this setup. It can be at different levels, but we're going to keep the isocenter to be the same point right here. So that reflects the practice of how treatments are done. So let me draw here a dose versus depth plot, and then I'm going to show you how we would measure this and build it up. So I like to keep this practical. So let's draw here a box. This is going to represent the water phantom that you're going to acquire data in. So you fill this thing up with water. This is how we actually measure these curves. So let me draw a line here. I'm filling it up to this level just above the isocenter point. Okay, let's fill it up with water. Measure the dose at that point with a chamber, and here's your value here in this curve. So that gives you something near the surface. Let's fill it up a little more. We take another measurement. It's up here. Fill it up a little bit more. Measurements a little bit higher. Remember, this is the buildup region, right? So as we fill up, the dose is getting higher. And it gets up here. Now this point is actually that special point. That's the D max point, the point where the dose is maximum. But let's keep filling the tank up, right? Keep doing measurements. So fill, measure, okay? And as I fill it up, I'm building up this depth dose curve here, point by point. And now it's falling off because of the attenuation, right? So I can draw a smooth curve through here and connect points, and that's how you actually do the measurement. Now, you'll see here that since the point of measurement is not moving, there's no inverse square effect, right? It's sitting at the isocenter point, and the only thing that's changing here is the attenuation. So we took out that inverse square effect. All right, now if we define this maximum point here as 1, renormalize it, then this, instead of dose, this is now the TMR. So tissue maximum ratio. So TMR is just defined as the dose measured at some depth D, and I showed you how the setup, and we just measure it, divided by the dose measured at a depth of D max. That's just the definition of TMR, how it's defined. And importantly, this is as measured at this isocenter point under the setup I just showed you. And so now we'll see how TMR is used in a few minutes, but that's just what it is. Also, you'll sometimes hear about this TPR, tissue phantom ratio. It's the same kind of concept, except now it's the dose at a depth of D divided by the dose of some reference depth, reference depth. So it's the same concept. It's just instead of using a reference depth of D max, you're using some other reference depth. And sometimes people use this for various things. But TMR is the main thing to know about. So there's one more thing to mention about TMR before we go on, is that like PDD, TMR will also depend on various parameters of the beam. So as the energy of the beam gets higher, the TMR falls off more quickly, just like PDD did. The Dmax depth is deeper, just like it was for PDD. Also, there will be a field size dependence. So for larger field sizes, the TMR will be larger because of the scatter effect. All those same physical processes are there. All right, so those are the basics of TMR, TPR. which are most useful for isocentric treatments and calculations. I'll leave you with a little bit of further reading here. And then in the next video, we're going to get into what you do with this. How do you use a TMR to do a dose calculation for programming the machine to deliver a certain dose and to calculate dose in different points in a patient. Thank you.